folks, I hope you're doing well today. I want to talk about properties of limits in this video, and I'm going to give you quite a few theorems about properties of limits, but the great thing about this is it's going to make it easier to calculate limits. If you'll recall, so far we know how to calculate a limit graphically, which means we look at a limit and we get closer and closer to the specified x value to figure out what the y value is doing, or the f of x value. Or we can do it numerically by setting up like a table and substituting in values closer and closer and closer to the c value. It would be so much easier if we could just do what we call direct substitution and just plug the c value into the function. And there are times where we are allowed to do that, but we have theorems that back this up. And the first theorem here has three different properties that will come in handy. So notice it says Theorem 1.1 basic limits. So let b and c be real numbers. So b and c are just any number that you could think of as long as it's a real number. And n is going to be a positive integer. So notice the first one that says if you take the limit as x goes to c of just a number, in other words, this is a constant function, your answer is going to be that number. Now, we could do a proof of this, and I may do a proof of some of these, but I really just want to spend some time getting you to understand what the theorem says. If I graph this first function, I'm graphing just a number, and that's a horizontal line, right? It's a horizontal line at y equals b. So, of course, if c is something down here, then the y value, or the limit value, is going to be b. You could look at the graph and tell that's going to happen. Next, you know what the graph of y equals x looks like. It's a straight line, goes through that perfect diagonal. So if this is c, and I go up and meet the function, turns out that's c as well. So, I mean, you know, your x, it's like you're plugging in c into your x value, and it's going to give you c. And then this one, now, I can't graph that because it could be x squared, it could be x to the third, it could be x to the fourth. So this third property here is really powerful, but it's saying that whatever your c value is, you just substitute it into the function, and it's going to give you the answer. And I have an area over here for proofs. The first two are pretty easy to prove. The third one, not so much. It comes from later properties. But let's just take a look at proving the first one. So for number one, remember, to do a proof, you've got to do a little bit of scratch work. You've got to figure out what delta needs to be in terms of epsilon. Well, it works out well for this one to just let delta equal epsilon. Okay, and then remember, you're using that definition, and so you say for every epsilon greater than 0, there exists a delta equal to epsilon, such that when 0 is less than the absolute value of x minus, now c in our problem is c, is less than delta, then you do that absolute value of f of x minus L is equal to the absolute value. Now, f of x in our problem, remember we're doing number one, is b, minus our L in our problem is b, right, which is equal to 0. And that's definitely less than delta, which is equal to epsilon. Okay, that's a weird proof, but basically that's how that works. Now, for the second one, it works out well actually to do this again. Let delta equal epsilon. So how about you just assume, okay, we're going to let delta equal to epsilon. And the line that we have above here, so for every epsilon there exists such that 0 is less than x minus c is less than delta, then, okay, then we're good to go. Let's go ahead and start there. We have the absolute value of f of x minus L is equal to, now f of x in this problem is x. Our limit in this problem is c. Well, remember, it's a given that that's less than delta, which is equal to epsilon. And that is the end of that proof. Okay? So again, I think it's awesome if you can do the proofs and you can understand and follow all that, but it's more important, the big picture, I need you to graphically be able to imagine what's going on here. So, real quick, notice, again, this is a constant function. Anytime you take a limit of a constant function, notice there's nowhere to plug the 3 in. That answer is just that constant. Okay? Next problem, this is number 2, it represents that. If you have just a basic f of x equals x function, you can take that 2 and just plug it in, and the answer is 2. And then a third situation, again, we call that direct substitution. If we're taking the limit as x approaches negative 1 of x to the third, I can write this as negative 1 to the third, which equals negative 1. So you don't have to graph or get closer and closer and closer to the value. You can actually perform direct substitution on these 3 types of basic limits. And we also have Theorem 1.2, which has 5 different parts, and this is quite a powerful theorem. So notice well, first of all, let's read the conditions. B and C are going to be real numbers again. So B and C could be any real number, not a variable, they're numbers. N is a positive integer, and that means it's going to be an exponent. Let f and g be functions with limits. So keep in mind, f, the limit is x goes to c of f of x has an answer, it's L. So it can't be a does not exist problem. It has to have a limit answer. And the limit is x goes to c of g of x is equal to some other value, k. Now, here's what's important. For number 1, the scalar multiple rule. Notice what happens. And I'm going to write it in between. I think more important than doing proofs, I'm going to write out here kind of an in-between way to think about this. So if you take the limit as x goes to c of b times f of x, my PowerPoint was freaking out. Did you see that? You are allowed to pull the b out front. That is a scalar multiple, often called a constant multiple. It means the same thing. That's b times the limit as x goes to c of f of x. And then we were given that answer. So that's b times, and it's right up here, it's L. So in other words, you're always allowed to move a constant multiple in front of the limit sign. Number 2 is the sum or difference. If you're adding 2 functions together, you can take the limit of these separately. So this is equivalent to saying the limit as x goes to c of f of x, and then separately plus or minus calculate the limit as x goes to c of g of x. So you can split this up as 2 separate limit problems. You can do the same thing with the product. This is number 3. If you have this statement, you can write that as the limit as x goes to c of f of x times the limit as x goes to c of g of x, which would just equal to L times k, just like this one would equal to L plus or minus k. Look, if you're dividing, you can take those separately as well. So if you have the limit as x goes to c right here of f of x divided by g of x, you could write that as the limit as x goes to c of f of x divided by the limit as x goes to c of g of x, as long as your limit as x goes to c of g of x is not equal to 0. You can do that. And then finally, if you have, look at that, that's raising a function to a power. You could write number 5 as the limit as x goes to c of f of x. Take the limit first and then raise it to the power. And then that would give you that L times n. Now, if you're not used to reading these mathematical theorems, this might not mean a lot to you. But when you see this problem in action, okay, some of these problems you'll go, oh, okay, I get what she's saying. So just stand by for a minute, you'll get it. So I have a problem right here for you. Notice I kind of shrunk up the property, but this is that theorem 1.2, which means we can pull a scalar out front if you're adding or subtracting different terms. You can split those up. If you're multiplying two functions together, you can take the limit of each of those separately. If you're dividing, you can split it up. If you have a power, you can put it on the outside. So first thing I want you to notice here is there's three separate terms. So I'm really taking the limit of this entire polynomial is what this is. But I could split it up using the sum difference rule. So first I'm going to use the sum difference rule. And I could write this as the limit as x goes to 7 of 5x to the third plus the limit as x goes to 7 of 2x minus the limit as x goes to 7 of 6. So you see what I did? I split that up into sum difference, three different sum and differences. Then you know what we could do? We could use the scalar multiple rule. And I could pull these scalar multiples in front. So this 5 can be moved in front. This 2 can be moved in front. Now this 6 is a constant. That's a different rule. We'll handle that in just a minute. Okay, so now I have 5 times the limit as x goes to 7 of x to the third plus 2 times the limit as x goes to 7 of x minus the limit as x goes to 7 of 6. Now, let's go back to our original theorem 1.1. Number 3 said you can do direct substitution when you have an x raised to a power. That was the third one. Not 3 here, but let's go back. Number 3, right here, says that I can just take my 7 and plug it directly into my x to the third. Okay? And then take a look at the next one. That's number 2 on that same theorem that says whenever you have just an x to the first, you can plug your number directly in. And this is number 1 in theorem 1.1. So again, if I go back to theorem 1.1, number 1 says if I have a constant, then my answer is just that constant. Oh, I went too far. There we go. All right, so what I can do is I can take, I have 5 times, and I take that 7 and I plug it in. So 5 times 7 to the third plus 2, and I can take that 7 and plug it in. Minus, and I can take that 7, but wait a minute, that's a constant. There's nowhere to plug it in, so the answer to that is just 6. And that came all from theorem 1.1. All right, then I just calculate it. So 5 times 7 to the third equals 5 times 343, which is 1,715. Plus 2 times 7, of course, is 14. So plus 14 minus 6. And I add 14 to the 1,715, and then I minus 6, and I get 1,723 is that limit value. Okay, now there's something really important going on here. Do you notice what happened? Please tell me you notice what happened at the end. I mean, I split it up. I used the sum difference rule. I used the scalar multiple rule by pulling the constants in front, and then I used theorem 1.1, all 3 parts of it. I used a lot here. It's like 1, 2, 3, 4, 5, 6 different properties, maybe even more than that. But essentially, all I did was take that 7 and plug it in the function. That's all I did. When that brings me to the next theorem. So check out this theorem right here. It says theorem 1.3, limits of polynomial and rational functions. what we just had in that last problem was a polynomial function. It says if p is a polynomial and c is a real number, then all you have to do is plug the c value into the polynomial. Isn't that awesome? One of the easiest things you could possibly do. So to find the limit of a polynomial, you just plug the limit value or the c value directly into the polynomial, just like we did on this problem, except we could have done it right at the beginning. We just didn't have the theorem yet, so we had to use all of those other properties to get it done. Something else that's pretty powerful, if you have a rational function, then what you can do is the same thing. If you take the limit as x goes to c of your rational function, then you can simply just plug c into your rational function. Here's the thing though, you cannot have a 0 in the denominator, so please keep this important point in mind. If you would take c and plugged it in here and it gave you 0, then we would have to reevaluate how to do that problem. Okay, so got another example for you. Here you go. This is what the homework is going to look like. So they want us to find the limit of a rational function. So the first thing you want to do is just to try to do direct substitution. Just plug it directly in. So this would equal to 2 squared minus 2 divided by 2 plus 1. And I simplify. So 2 squared is 4 minus 2 divided by 3. We know 4 minus 2 is 2. 2 minus 2 is 0 divided by 3. And we know 0 divided by 3 is 0. So the limit is just 0, which is much easier than trying to graph that function or substitute 3 or 4 values on each side of 2 into the function. But you've got to make sure when you do this substitution thing that you do it properly, that you're following the theorems. And again, the theorem says if you have a rational function, and a rational function means you have a polynomial in the numerator and a polynomial in the denominator, and when you plug in, you don't get a 0 in the denominator. By the way, a 0 in the numerator is fine. A 0 in the denominator, which we did not have this time, is not fine. Here's another super nice theorem to have. Theorem 1.4, limits of functions involving a radical. Look what this says. It says if you have a radical, you know what a radical is, a square root, a cube root, a third root, a fourth root, whatever. I said cube root and third root, they're the same. You take the limit as x goes to c. And all you do, again, direct substitution, you take the c and you plug it directly into the function. Now, notice at the bottom, this is important, it says is valid for all c values if n is odd. So if you have a cube root, a fifth root, a seventh root, a ninth root, if n is an odd root, then c could be positive or negative, it doesn't matter. But now if n is an even root, square root, fourth root, sixth root, then c has to be greater than or equal to 0, right? Because you can't take the square root of a negative number and get a real answer. And all this stuff that we're talking about are real valued answers. We're talking about graphs, so we're talking about real numbers. So here's a problem. Find the limit as x goes to negative 8 of the cube root of x. Now my question is, can we plug the negative 8 directly in? Is it okay to take the cubed root of negative 8? Well, this says as long as n is odd, cube root, then you can plug in any c value, positive or negative. And we can. What's the cube root of negative 8? You know what that is. It's negative 2, right? Because negative 2 times negative 2 times negative 2 is negative 8. And there we go. Limit is that simple. If you can substitute directly, you are allowed to do that with the theorems that we have so far. Now here's an interesting theorem, composite functions. You know what a composite function is? Is when you have a function inside another function. You learned about this in your pre-cal class. So if I take a function like, 5x and put it inside the sign, that's a composite function. Your inside function is 5x, your outside function is sign. Now this theorem says if f and g are functions such that the limit as x goes to L of f of x is f of L, in other words, you are allowed to plug L directly into your function, then you can say the limit as x goes to c of f of g of x. So you plug a function inside another function. That's the same as taking the limit of the inside and then plugging that into the outside function. So the question here is, when we look at this problem right here, okay, the question really to you is, are we allowed to take the limit as x goes to negative 2 of x squared minus 4? And I'll write down exactly what I'm saying. So, am I allowed to put the square root on the outside and take the limit as x goes to negative 2 of x squared minus 4? In fact, as we can, because this is a polynomial. And remember, polynomial functions, you can do direct substitution. So my next step would be to evaluate that first, and then take the square root of it. So I have the square root of, so this is going to be negative 2 squared minus 4, which is the square root of negative 2 squared is 4 minus 4. The square root of 0 is 0. Nothing wrong with 0 as an answer as long as it's not in a denominator. So that's our answer, is 0. Alright, so here are those trig functions I've been promising you. And this is a very easy theorem. How many trig functions are there? 6, right? Notice there are 6 different parts of this theorem. It says the limit as x goes to c of sine of x is sine of c. What did we do? We just took that c value and plugged it right in there. No problem, right? Actually, we didn't plug it in there. That's after we plugged it in. We plugged it in right there. And we got the sine of c. The limit as x goes to c of cosine of x. What do? We just take that c and plug it in, and we evaluate. For tangent, we just take that c and plug it in, and we evaluate. And the same for the other 3 as well. But here's something I want you to notice. I underlined this. I'm about to highlight it because it's very important. C has to be in the domain of the given trig function. Now, sine and cosine, their domain is all real numbers. You can plug in any value you want to sine and cosine. If you think about their graphs, they cover everything, right? Their sine and cosine look similar, just scoot it over, and in the other direction as well. But now, tangent, cosecant, secant, cotangent, they have a specific domain. Not every value can be plugged in. Remember, tangent is defined to be sine over cosine. So any value that would make cosine equal to 0, like pi over 2 or 3 pi over 2, you're not allowed to directly substitute into tangent. So be careful. This doesn't mean you can plug in any number you want. It has to be in the domain of the trig function. If it's not, then you probably have a limit that doesn't exist. So how about this problem? Well, is pi in the domain of tangent? Well, all you got to do is just plug it in to find out. So I'm going to write the limit, but I don't really need to. This is just going to be tangent of pi by direct substitution. Now we need to be able to evaluate that. Some of you do like I do. I just think about that as the sine of pi over the cosine of pi. And we know that the sine of pi, if it helps, remember your unit circle. Your pi lives right over here. Sine is the y value right over here. Y value is 0. Over the cosine of pi, the x value right over there is negative 1. Or you could use your calculator. 0 divided by negative 1 is 0. Remember, if you use your calculator, you need to be in radian mode. These are radians, not degrees. Now, here's a theorem you're going to use a lot. The other ones you will too. Theorem 1.7, functions that agree at all but one point. So notice it says let c be a real number, as it always is. If f of x equals g of x for all x not equal to c in an open interval not containing c, and if the limit of g of x as x approaches c exists, then the limit of x goes to c of f of x is the same as the limit as x goes to c of g of x. The best way to explain this problem, or this theorem, is actually to use a problem. I want to show you something. So this is a rational function, right? So there's a theorem that says if you have a rational function, you can just substitute directly this value in, except for one situation. But let's go ahead and do it and try. So I'm going to have 3 times negative 2 squared plus 5 times negative 2 minus 2 divided by negative 2 plus 2, which is going to give me a value of negative 2 squared is 4, right? 3 times 4 is 12 minus 10 minus 2 divided by, we have a problem. Negative 2 plus 2 is 0. If you have a 0 in the denominator, you cannot do direct substitution. Even if it's a rational function or polynomial, well, polynomial you won't have a 0 in the denominator, but for a rational function you can't do it. 12 minus 10 is 2, minus 2 is 0 divided by 0. I'm going to put quotes around this because this is important. If you ever get a 0 over 0, that means you must simplify the problem. So what this theorem says is that if you have a function that can be simplified, you need to simplify it, and the limit of the simplified function is the same as the limit of the original function, because they agree at every place but one value, okay, or maybe the c value. So what do I mean here? Well, we've got 3x squared, I'm rewriting, plus 5x minus 2 divided by x plus 2. Now 3x squared plus 5x minus 2 factors. Now some of you know how to factor it just real fast, nothing to it. One of the factors is x plus 2. The other factor would be, what, 3x minus 1? But some of you are not so good at that. So what I want to do, this is all about the algebra, right? I want to take a minute and factor this polynomial using a method that some of you know. What you can do is multiply 3 times 2 together, 3 times negative 2, and find numbers, I'm going to do this at the top of the page, that multiply to equal negative 6. And again, the negative 6 came from 3 times negative 2. And at the same time, you need numbers that add to be 5. Now, are there numbers that do that? Well, sure. How about a positive 6 and a negative 1? They multiply to be negative 6 and they add to be positive 5. Now, here's what you got to do. Next is factor by grouping. So you rewrite your problem, the 3x squared you keep. You're replacing the middle term 5x with the two numbers you found. So it's going to be plus 6x minus 1x and then minus 2. So notice the first term and the last term stay exactly the same. The middle term of 5x gets replaced with the two numbers we found, of course, times x, so it would equal 5x if we added it back together. Now what's next? Factor by grouping. So these first two, I factor out a 3x. That leaves me with x plus 2. Here I factor out a negative 1, which must leave me with the same thing in parentheses, x plus 2. And then you factor the common x plus 2, and that leaves times 3x minus 1. Okay? So if you're struggling factoring trinomials with leading coefficients that aren't 1, that's a method that works every time. Okay, if it'll factor, that'll work. I'm not saying you have to do it that way, I'm just saying if you get stuck. Now the x plus 2's cancel. So our function, 3x squared plus 5x minus 2 over x plus 2, is equivalent to just plain old 3x minus 1. So what they're saying is I'm allowed to take the limit as x approaches negative 2 of just 3x minus 1 instead, because these are the same function, but they differ at one point at negative 2. Because it canceled out, it gives us a hole in the graph, okay? So I have 3 times negative 2 minus 1. That's going to be negative 6 minus 1, which is equivalent to negative 7. All right? But now, to know that you need to do that, you could always just try to substitute. And if you get 0 over 0, you're going to have to simplify that rational expression. And then try again. So here I have a strategy for evaluating limits. This is not a theorem. This is just something to help you work through these problems. says learn to recognize which limits can be evaluated with direct substitution. So we know that any polynomial can be evaluated with direct substitution. In other words, you take the c value and you plug it in. A rational function can be evaluated with direct substitution unless you get what we got just a minute ago, 0 over 0. Then you should simplify first. So that's what number 2 is saying. For a function that cannot be evaluated by direct substitution, simplify it. And then use a graph or a table to back up your conclusion. So let's just say you're not really sure if you did it right or not. Then plug in numbers closer and closer to the c value on both sides and see if you don't get the same answer. It's nice to have 3 different methods of calculating the limit. So if you feel uncomfortable, you can always try one of those other methods. Now, compare these 2 limit problems. Okay, they look very similar, don't they? Matter of fact, they only differ by a sign. You got x to the third minus 1 here, x to the third plus 1 here. So the first thing I would try is direct substitution. So if I plug in 1 directly, I get 1 to the third minus 1 over 1 minus 1. Well, 1 to the third is 1 minus 1, which is 0 over 0. Aha! What does that mean? Simplify. That did not work. Okay, so you just mark through it and go, nope, that wasn't the right way to do it. This will simplify. So I'm going to take the limit as x goes to 1, x to the third minus 1 factors. A lot of you may not remember that's a difference of cubes, and a difference of cubes factors into the cube root of x to the third goes in the first spot, the cube root of 1 goes in the second spot, and whatever operation, which is minus, goes here. Next, you're supposed to square the first term, change the sign, multiply x times 1 together, which just gives you x, and then square the first term added. Okay? There's a formula for that. Divided by x minus 1, and then there you go. That's the reason you got 0 over 0, because those cancel, and you were trying to plug 1 into this function. Now, this function, x squared plus x plus 1, and this function, x to the third minus 1 divided by x minus 1, are the same function except at one point. At x equals 1, there's a hole in this graph where there's none in this graph. Okay? But we're allowed to plug 1 into this one because of the theorem we had a minute ago. So this is equivalent to 1 squared plus 1, which is 3. So the limit to our function there is 3. Now this problem, if I take 1 and plug it directly in here, that would give me 1 to the third plus 1 divided by 1 minus 1, which gives me 2 over 0. Now a 2 over 0 is probably not going to simplify. A 0 over 0, I promise you will. A 2 over 0 is not going to work. As a matter of fact, you can expect this to be a D and E. Now, to feel confident about y, you may want to plug in numbers closer and closer to 1. Or you could look at the graph. You could always type this into Desmos or your graphing calculator and quickly look at the graph for this thing. If I plug in numbers closer and closer to 1, okay, let's just try that. Let's just plug in. I want you to see this. So let's just plug in 0.9, 0.99, 0.999. Okay, it's going to take a minute. This is like my t-table, so that's my x value. Let's figure out what my y answer is. Alright, so I took a minute and I just plugged these x values that are closer and closer to 1 just on the left side into my function. And look, so I got a negative 17.29 when I plugged in 0.9. I got a negative 197.03 when I plugged in 0.99. And a negative 1,997 when I plugged in 0.999. What does it look like is happening? Well, they're getting smaller and smaller, right, or bigger and bigger negative numbers. So this is going to negative infinity, which basically backs up my does not exist guess right there. But when you have a does not exist, in other words, you have a non-zero number over 0, it helps to go with a different method, either numerical or graphing, to back yourself up. But if you get 0 over 0, that can be simplified. So I want to show you one more type of problem before we take a break and I go to part 2 of this video. This is one of those problems that we're going to need to simplify because we can rewrite this as a function that differs from this function only by 1 point. How do I know? Well, plug 3 right in. Just plug in 3 and see what you get. So I've got the square root of 3 plus 1 minus 2 divided by 3 minus 3. And you already see in the denominator we have a problem, okay? But we don't know what kind of problem we have until we do the numerator, simplify the numerator as well. So that'd be the square root of 4, which is 2 minus 2. So once again, I have a 0 over 0 situation, which is screaming to simplify. But the thing is, how do you simplify something like this? It's not like you can factor and cancel. So I'm going to show you a technique that works often, not 100% of the time, but when you have a square root in your problem and you have a 0 over 0, this technique should work. And what you're doing is you're multiplying by a conjugate. So watch this. I know in the end I'm going to take the limit, but right now I'm just going to focus on the function part. So I have the square root of x plus 1 minus 2. Right now I'm rewriting over x minus 3. So what I'm going to do is I'm going to multiply by what's called a unity fraction, which just means it's equivalent to 1. So I'm not changing the value of my expression. So I'm going to multiply by the conjugate of the numerator. Now, sometimes it's the conjugate of the numerator, sometimes it's the conjugate of the denominator. How do you know which? It's the one with the square root in it. So I'm going to multiply by the square root of x plus 1 plus 2. So notice I changed this operation. And in the denominator by exactly the same thing. Why? Because you're only allowed to multiply by 1. So you multiply by the same value in both the numerator and the denominator. Now here's where those algebra skills come into play. I'm going to distribute the top. So I'm going to multiply the square root of x plus 1 times the square root of x plus 1. That's just going to give me x plus 1, right? No more square root, because it's the square root of x plus 1 squared. Now I'm going to multiply the square root of x plus 1 times 2. So it's going to be plus 2 square root of x plus 1. Now I'm going to multiply negative 2 times the square root of x plus 1. And then finally negative 2 times positive 2, which is negative 4. Okay? So again, it's all about these algebra skills. So I used the FOIL method. I did first times first, which gives me this. For outers, so square root of x plus 1 times positive 2 is this term. The inners, negative 2 times square root of x plus 1 is the third term. And finally last, negative 2 times positive 2 is negative 4. Now in the denominator, I don't want to FOIL that right now. I'm going to keep it just factored for the moment. X minus 3 times the square root of x plus 1 plus 2. For some reason later I need to multiply that out, I can, but remember what my goal is? My goal is to get this x minus 3 to cancel out, so I don't want to multiply that out right now. I keep going. In the numerator, look what I've got. This 2 square root of x plus 1 cancels with this minus 2 square root of x plus 1. This is the reason why we multiplied by the conjugate, so that would happen. So now I have x plus 1, parentheses not really required, minus 4, over x minus 3. Because remember, I don't want to multiply out the denominator, not yet anyway. Look, x plus 1 minus 4 is x minus 3 over this x minus 3 times the square root of x plus 1 plus 2. Now, what I wanted to happen now is going to happen. This x minus 3 is going to cancel. And now I have 1 over the square root of x plus 1 plus 2. Now how does that help? This function and this function are the same function except at one point. At x equals 3, the one that canceled out, okay? X minus 3 is the factor that canceled, but x equals 3 is the 0 for that. That canceled out. Therefore, I'm allowed to substitute 3 into this function, whereas it gave me a hole in the graph for this function. So now instead, I'm going to take the limit as x approaches 3 of 1 over the square root of x plus 1 plus 2. And I plugged 3 directly in. So it would be 1 over the square root of 3 plus 1 plus 2, which is 1 over the square root of 4 plus 2. We all know the square root of 4 is 2 plus 2, which is 1/4. What do you think about that? I always have to do a few of those because that kind of blows people's minds. But there it is. I will do more in class or on other videos if you like. But that is the trick for those square root problems. But now promise me you will always just take that number and plug it in first just to make sure you can't do it. Because I'd hate for you to do all that work and you could have just plugged in a 1 or something. Like if I change that, the limit as x goes to 3. If I change it to the limit as x goes to 1, you can plug the 1 right in, no problem. So try that first, and if it doesn't work, then you resort to these simplifying techniques. All right, that's the end of part 1. I'm going to come back for a part 2 for this section, which is properties of limits. It'll be a shorter video. Have a great day.